Okay, let's review some of the concepts by doing this problem set. And let's start with question 1. So in samples we deal with blank, in populations with blank. So in samples we deal with statistics, and in populations with parameters. So which of the following provides a measure of central location of the data? Standard deviation? No, that's dispersion. Mean? Yeah, that's correct. And variance and range are matters of dispersion too. A numerical value used as a summary measure for a sample. A numerical value used as a summary measure for a sample, such as a sample mean, is so for a sample, we deal with statistics, so it's a sample statistic. Since the population size is always larger than the sample size, then the sample statistic can never be larger than the population parameter? No. Can never be equal to the population parameter? No. Can be smaller, larger, or equal to the population parameter? That is correct. So just think about if you have a statistic like the maximum, then you have like 5 observations, or let's say you take the minimum, then it's easy since the population size is always larger than the sample size. The sample statistic, yeah. So let's say if I have a population of 1, 2, 3, 4, 5, so the highest value, the maximum would be 5, but if I have a sample of only numbers 1, 2, 3, then the maximum value in the sample would be 3, which is less than. And if I ask for the minimum, let's say the minimum value in this, let's say the population is 1, 2, 3, 4, 5, but then I have a sample of 3, 4, 5, well then the minimum is 3, which is greater. So it is C. So this is the sign for mu, and that is whenever we use Greek letters we deal with parameters. So that is typically used for the is an example of a population parameter, and specifically the population mean. The median of a sample will always equal the mode, the mean, the 50th percentile, or all of the above. Now the median is the midpoint, that's the 50th percentile. The median is a measure of relative dispersion, absolute dispersion, central location. Of course, that is central location. The 75th percentile is referred to as the first quartile, no, that's the 25th. Second quartile, that's the 50th. It's the third quartile. The pth percentile is a value such that at least p% of the observations are less than or equal to this value. So again, if you take a test and you are given your percentile, and let's say your percentile is 95%, that means 95% of all the people who took the test are either worse than you did or have the same score. The first quartile contains at least 1/3 of the data elements. No. Is the same as the 25th percentile, that's correct. And C and D is the second and the third quartile. Which of the following is not a measure of central location? Mean, no. Central location. Median, central location. Variance, not variance is not central location. And the mode is also one of locality. 12. If a dataset has an uneven number of observations, the median cannot be determined. No, in statistics everything can be determined somehow, or most of the things. Is the average value of the two middle items, that's correct, must be equal to the mean. No, that's nonsensical. Is the average value of the two middle items when all items are arranged in ascending order. Yeah, that is even more correct than B. So whenever we calculate a percentile or the median, we need to make sure that the data is sorted typically in ascending order. The most frequently occurring value of a data set is called the mode. Okay, if index I, which is used to determine the location of the pth percentile, is not an integer, its value should be rounded up. And that is at least the case when we use that simple textbook approach. The mathematically most accurate statistical descriptive measure of the location of a data is the mean. And again, the mean makes it the mathematically most accurate measure of central tendency because the sum of all the deviations from the mean are then 0. Which of the following symbol represents the mean of the population? We already said that earlier, that's that Greek letter mu. Sigma squared, the first one would be the variance, sigma the standard deviation, x bar the sample mean. So which of the following represents the mean of the sample? Well, that's x bar. Which of the following symbols represents the size of the sample? So the sample size is typically lowercase n, the population size is large N. Okay, so the hourly wage of a sample of 130 system analysis are given below. The mean is 60, the mode is 73, the median of 74, and the range is 20, and the variance is 324. So the coefficient of variation. So the coefficient of variation is again defined as a relative risk measure which captures the ratio of the standard deviation relative to the mean. So the mean is 60 and the variance is 324. So taking the square root of 324, that should be 18 if I remember correctly. So let's quickly double check. So that's 18, and then we have to divide 18 by 60, and that should be 0.3. So which is 30%. The variance of a sample of 169 observation equals 576. Okay. The standard deviation of the sample equals 10. Well, the standard deviation is simply the square root of the variance. So we don't really have to worry about the sample or the number of observation. That's irrelevant. So we have to take the square root of 169, which is 13. The difference between the largest and the smallest data values is that's obviously the range. Which of the following is a measure of dispersion? Percentiles, no. Quartiles, no. Yep, interquartile range. The interquartile range is the 50th percentile, no, that would be the median. Another name for the variance, no, that's silly. The difference between the largest and smallest values, no, that's the range. The difference between the third and the first quartile, so D is correct. When the data are skewed to the right, the measure of skewness will be positive. When the data is positively skewed, the mean will usually be greater than the median. So the mean is very much affected by outliers. Which of the following is not a measure of dispersion? That's the 50th percentile, the median. The interquartile range is used as a measure of variability to overcome what difficulty of the range? Well, the range is obviously highly affected by outliers. So the sum of the range variances is 0. No, that's silly. The range is difficult to compute. No, that's not the case. The range is influenced too much by extreme values. That's correct. So the interquartile range basically gives you the range where you find the middle 50% of all observations. If the variance of a dataset is correctly computed with the formula using n-1 in the denominator, which of the following is true? The dataset is a sample, yeah. The dataset is a population. The dataset could be either a sample or a population because, typically that's what we do because it is. I can apply the formula to whatever I want to, I guess. So that's maybe not the best question. So let's move on to 29. The measure of dispersion that is influenced most by extreme values is, of course, the range. But then the variance and the standard deviation, they would be second, and the interquartile range would be the least affected. The descriptive measure of dispersion that is based on the concept of deviation about the mean, well, we talked about that earlier. That's the descriptive measure of dispersion that is based on the concept of a deviation about the mean is the standard deviation. So again, the variance is the average squared deviation from the mean, and the standard deviation is the average deviation around the mean. The numerical value of the standard deviation can never be larger than the variance. No. 0, well, it can be never negative because everything is squared. The sample variance is always smaller than the true value of the population variance. Now, it could be smaller, equal to, or larger than. The variance can never be 0. No, it can be 0. Can never be. So no, the variance can never be negative either. If two groups of numbers have the same mean, then their standard deviation must also be equal. Now that's silly. Their medians must also be equal. Also silly. Their modes must also be equal. That's all silly. So D, none of the alternatives is correct. The sum of deviations of the individual data elements from their mean is always greater than 0, always less than 0, sometimes greater, sometimes less. No, it's always equal to the 0. So the sum of all the deviations from the mean is always 0. And then just to give you again an idea, So let me see if I can quickly pull up my tablet. So if we have, let's say, data, so what that means is, if we have, maybe that's not the best location, maybe start here. So if we have 3 observations and the values are, let's say, 2, 3, and 10, then the mean would be 5. 2, 5, 15 divided by 3 is 5. But now, if I subtract from everywhere the mean and I do xi minus x bar, 2 minus 5, negative 3, 3 minus 5, negative 2, 10 minus 5 is 5. So negative 3 plus negative 2 is negative 5 plus 5 is 0. So that is meant by what makes the mean the mathematically most accurate formula. Okay, that's just a numerical measure of linear association between 2 variables. So measure of relation is the covariance. And again, the formula for the covariance was the sum of the products of all deviations from the axis from their mean So that was the formula for the covariance, and if we divide the covariance by the product of the standard deviations of x and y, then we get the correlation coefficient. So positive values of covariance indicate a positive variance of the x values, a positive variance of the y values, that the standard deviation is positive. Now it must be D, that there is a positive relationship between the independent and the dependent variable. So I use this example. Let's say if you imagine you have a sample of people and you look at their height and their shoe size, then people that have an above average height, they probably have also an above average shoe size. So then we multiply something positive with something positive. But people that have a below average height, they also have a below average shoe size. Then we multiply something negative with negative. So we get ultimately a positive relationship. And if something corresponds that is above the average in one dimension but below the average in another, then we will get something which is indicating a negative or inverse relationship. A numerical measure of linear association between two variables is the correlation coefficient. So the correlation coefficient, which is sometimes just R, is the covariance between x and y, which we calculated earlier, divided by the standard deviation of x times the standard deviation of y. The coefficient of correlation ranges between 0 and 1. No, it can be negative, but it is limited between -1 and 1 as a result of that standardization. Minus infinity and plus infinity, no, that would be true for the covariance, but not for the correlation coefficient. The coefficient of correlation is the same as the coefficient of determination. No, that's something else. Can be larger than 1, cannot be larger than 1. Yeah, cannot be larger than 1, because it is between -1 and +1. So during a cold winter, the temperatures stayed below 0 for 10 days. The variance of the temperatures of the 10-day period is negative, since all the numbers are negative. No, because we square it. So again, the standard deviation is the square root of the variance, and the variance is the sum of all the squared deviations from the mean over n-1. So let's say if the mean was -5, now I have -10. -10 minus -5 is minus minus, it's -5, but then we square it, so everything becomes positive. And of course we still need to put the square root around. So it must be at least 0, and it would be 0 if the temperatures had been -5, -5, -5. So if there was no variation in the data. Since the mode is the most frequent occurring data value, it can never be larger than the mean. No, that sounds silly. Is always larger than the median? No. Is always larger than the mean? No, in statistics there's never anything that's so deterministic between the various measures of central tendency. Okay, so maybe let's stop here so that the video doesn't get too long, and then let's work with some more comprehensive problem sets in the next video.